Hello friends, I am Dr. Nitin Saxena. In this lecture, we will define the Gauss law which can be used to find the value of electric field for any surface. This, like we have already studied the electric flux concepts, electric field concepts, and like by integrating or by like we have these some point charges and then we can find using the formula 1 upon 4 pi epsilon naught q upon r square, and this give the value of total electric field for point charge. Now the question comes when we have some continuous charge distributed surface, which we have discussed in previous lecture, that if the surfaces are like this, that the charge is not confined on a single point, the charge is distributed uniformly, like linear charge, surface charge or volume charge. In those type of cases, the calculation for electric field becomes very easy with the help of Gauss law. So first we will try to understand what is Gauss law, where we can apply the Gauss law, and finally we will see some specialized figures or specialized charge distributed surface for which we will try to find the value of electric field with the help of Gauss law. Okay, so let us see what is the Gauss law. So Gauss law is defined, the Gauss theorem, or we can say Gauss law, we can define simply that for any surface, for any closed surface, the value of electric flux is given by q upon epsilon naught, right? Where q is the charge closed by the surface, right? This closed surface is called Gaussian surface. Since flux is defined as summation of E del A, so summation of E del A, right, is q upon epsilon naught, or integration of, if I right. So what we see here, we see that if we have a charged body, if we have any charged surface, then we will try to make a surface on this body, through like on the throughout of this body, and this we will make the surface, which surface is called Gaussian surface, right? Then the value of electric flux is given by the value is given by q upon epsilon naught, right? So if where the q is the charge which is enclosed, which is being enclosed by this Gaussian surface, all the charge will remain inside the Gaussian surface, right? And then we know that the value of flux is given by the formula summation of E dot dA del. So if we put the value of phi from here, so summation of E dot del A is given by q upon epsilon naught, and hence if we like replace this summation sign by integration sign, then the final theorem, mathematical expression for Gauss theorem will be this. Is it clear? Now, this is the theoretically what is the Gauss law. Now, let us see where we can apply the Gauss law first, and then we will try to solve some particular surfaces with the help of Gauss law. So, Gauss law is true for closed surface. No matter, like if we have something, suppose, so number one is the point is the Gauss law. Like in Gauss law, what we will do, we will try to make a closed surface and we will try to confine all the charge inside this surface. And it does not matter that what is the surface, like what is the physical property of the surface. It does not matter in Gauss law, right? The second is like the charge q which we have in the formula. Like what is the formula? I'm writing again. E dot del A is q upon epsilon naught. So this q is the charge which is confining in this surface, in this closed surface, right? For example, if I'm saying, okay, okay, the charge is distributed like this, right? The charge is on the surface of this metal, right? And if we are taking this as a Gaussian surface, so what we will say? We will say that the charge enclosed by this Gaussian surface is plus q. But if I am taking this as a Gaussian surface, then charge enclosed by this Gaussian surface is 0, because this plus q is lying on the outer surface of this metal body, metal sphere or maybe. Right. So we will see in this formula what is q. Q is the charge inside the Gaussian surface. It does not matter what is the total value of the charge. The charge may be plus q, and but we will write the value of q, the only that value of the charge which is inside the Gaussian surface, right? The next point is that whenever we are choosing a Gaussian surface, so we will try to make a surface in such a way that it must have the value of charge particle, right? So like if it is not possible to confine all the charge particle inside the Gaussian surface, then we will try to make that some part of the charge particle must come inside the Gaussian surface, right? So in this way, these are the some important points that we keep in mind when we are going for applying this law of Gaussian law. So let's see that how we can apply it. How can we apply it to find the electric field value for different cases? Okay, so first we see that we have a case. What is the case? The first case is the electric field due to an infinitely long straight straight uniformly charged wire. Okay. So, what is the question? What is the topic? That what is the value of electric field due to an infinitely long straight uniformly charged wire? Suppose I am saying, okay, I am saying this is a uniformly charged, this is infinitely long. This is infinitely long means this is going like this, okay? This is going like this. So I am taking a part. Suppose this is going infinitely like this. Infinitely long. From here also. It is going like this. So this is an infinitely long, straight, right? Straight, uniformly charged. Uniformly charged means this is a line charge surface. So if linearly charged surface, so we will define according to our previous discussion the linear charge density. Okay, so what is linear charge density? We define it with the sign, with the notification of sigma, right? So I am saying for this surface we have, okay, I am writing here sigma. And what is the sigma? The sigma is linear charge density. Okay, so the sigma is given to me, right? What is the value? Sigma? Sigma means charge per unit length. So linear charge density means charge per unit length. So for this infinitely long straight continuous wire, we know the value of charge per unit length. Right. Now the question is find the value at any particular point. At any particular point. Suppose I am saying the point is P. So find the value at point P using Gauss law. Okay. Question is clear. Now let us try to make a Gaussian surface around this charged surface in such a way that we will try to find the value of electric field at point P. So you see, if it is a linearly charged line, so the symmetrical this the for this the symmetrical surface will be slender, which I have already told you in my previous lectures that for any straight line, for any charged straight line, linearly charged wire, we can make a surface, a cylindrical surface, and the property of this cylindrical surface will be that at every point on the surface we have the uniform or equal value of the electric field, right? So like if I am saying, okay, if I am trying to make a surface like this which is passing through the point P, okay, which is passing through the point P, and now I want to know the value of electric field at point P. This is my question. Okay, and you see, when I am enclosing this linear charge inside this surface, so what you will get? You will get this surface as a Gaussian surface, right? Now for this Gaussian surface, if I apply the concept of Gauss law, then what I will say? I'll say, okay, the Gaussian surface Gauss law, according to Gauss law, this red figure, this slender, is a Gaussian surface, and E dot dA is given by Q upon epsilon naught, right? So you see, E is constant everywhere because I told you that this is a slender, and at every point of this slender we have the same value of E. This is the quality of this cylindrical surface, which is assumed as a Gaussian surface. So what we do, we can remember this point also. We will try to make a Gaussian surface in a way that all the points at Gaussian surface have the equal value of electric field intensity. What would be the benefit of this? The benefit will be this, that this E will become the constant, right? And if you see, if I am saying this is the positively charged, for example, so when you see this is the positively charged line, or it may also be negatively charged, but I am taking this positively charged line wire. So for this surface, the direction of area and direction of E will be same, right? You see, if I suppose this is the slender, so from this and this is the charged particle, so what will happen? The electric field will go, okay, let me draw with this pen. So the electric field lines will be like this, okay, axially. This is called axially. If this is like this, so it will go axially, okay. So when it will go axially, and this is the the area, so for this area the perpendicular direction will be this, and we know that the direction, the surface perpendicular, we show the direction of the area. So you see the direction of dA and direction of E is same. This means the theta between E and dA is 0, and if theta is 0, so cos theta means cos 0 will be 1, right? So what we can write here? We can write here E dA cos 0 is 1, so I am not writing it, equals to Q upon epsilon naught, right? So next step I can write E, since E is constant, I told you for the whole surface the value of E is constant. So E dA is Q upon epsilon naught. So at this particular point P, the value of E electric field intensity will be E. Now you see here, this is a slender. Suppose the length of slender, which is taken as Gaussian surface, is L, right? What I am saying? I am saying that this is the Gaussian surface slender, and for this slender which I am taking as a Gaussian surface, this length is L, right? And this point P is at a distance of R from this wire, and the point P is at distance R from wire, right? So this point P is at distance R from wire. Now you see, this is a slender, and for this slender, this dA is the area, is what? The area of the slender. What is the formula for the slender area? 2 pi r h, where r is the radius of the slender and h is the height of the slender. So you see here the 2 pi, okay, what is the r? The radius of the slender is r and the length of the slender is L. So the value of dA will be 2 pi r. Is it okay? Now you see what is the value of Q. So what is Q? Q is the charge which is enclosed inside this Gaussian surface, right? According to Gauss theorem, what is the value of Q? Q is the charge enclosed inside the Gaussian surface. So you see the charge per unit length is given by sigma. Total length is L. So total Q will be sigma L. This is okay. This is charge per unit length is given linear charge density sigma. So charge per unit length is sigma. The total length of the wire which is enclosed. I am not talking about the hole because hole is not enclosed. I told you earlier also that the part which is only inside the Gaussian surface, we will consider only that charge, and the charge inside this Gaussian surface is sigma multiplied with this length, so Q is L. So you substitute all these values here. So E 2 pi r L is sigma L upon epsilon naught. So E will be L and L cancel, sigma upon 2 pi r epsilon naught. Okay, sigma upon 2 pi r epsilon naught. So this will be the value of electric field at point P for a uniformly long straight charged wire. The point is clear. So in this way we can find the value of electric field intensity at point P for this particular wire, infinitely long uniformly charged wire, with the help of Gaussian law. The same, if it is clear, then we can move for the second surface, and second surface is, suppose we are taking sorry, we are taking the uniformly charged infinitely plane sheet. Here we have only line. Now what we are taking, electric field due to infinitely long sheet, plane sheet. Infinitely long plane sheet. Right? Plane sheet means, suppose like we have a surface like this board, a plane sheet, right? And the total charge is uniformly distributed on this board, right? So like let me draw a surface. The surface is something like this. We have a sheet. So suppose this is a sheet, and for sheet, you see, for this sheet, this is the two-dimensional figure. So what we will say, the total charge which will be uniformly distributed on this sheet as lambda. Suppose this is lambda. So what will be the lambda? Lambda will be surface charge density, right? Surface charge density. So the same question is what? That find the value of electric field. Find the value of electric field at, for this plane sheet. For plane sheet, find the value of electric field at any point P, right? Which is, suppose, at a distance r from this plate. Suppose I am saying the point is somewhere here P, and the distance is, suppose, r, right? So find the value of electric field at point P, which is at the distance of r from this uniformly distributed charged plane sheet, right? So how can I do this? The same philosophy I will use. What I will use, I'll use like, okay, I'll try to make a surface. I'll try to make a surface like this. Suppose okay. So I'm making a surface, a cuboid surface, okay, a cuboid surface like this, right? So you see, if I have the cuboid surface like this, so what will happen? Again, write E dot dA is Q upon epsilon naught. This is the what is this? Gauss law, right? So Gauss law, you see, first this is the Gaussian surface. Gaussian surface is a cuboid, okay, which is passing through this in this plane sheet. So the sheet is very long, so we are taking only this part, and I am saying this area, this one is A. This area is A, right? So if this area is A, so you see the electric field E and the area dA and Q upon epsilon. Well, first see what is Q. So Q will be, since lambda is the uh, surface charge density and this area is A, so the same area will cut to this plane sheet and this area will be same here also. So what we will say, that Q is lambda A, right? So the area, the charge confined with this cuboid surface will be lambda A, right? The total charge will be lambda A. Now you see the area, if we talk about the area and electric field, so what will happen here, you see, at point the electric field, this is, suppose this is, again I am saying plus charge, so what will happen, for this plus charge the electric field lines will go like this and like this also, okay. Because why it is going like this? Because this is the positively charged plate, so we will assume that its negative charge is at infinity, so it will go till infinity in both the directions. So since it is going in both the direction, so in place of writing E, we will write here 2E, and area is A, so 2EA is lambda A upon epsilon naught. When you will solve, you will get E is lambda upon 2 epsilon naught. This is clear? Because the electric field lines will go in both the directions. So we will take, in place of E, we will take 2E for this particular case. Right? So I hope this is also clear to you. Now next, see the next case, when we have to find the value of electric field for the three-dimensional figure. First we saw for the one-dimensional figure, then we saw for two-dimensional figure, now we are seeing for three-dimensional figure. Let's see what is the three-dimensional figure. So the three-dimensional figure is electric field due to electric field due to uniformly charged, right, thin spherical shell. Okay, electric field due to uniformly charged thin spherical shell. Suppose I am saying that, okay, this is a thin shell. This is a thin shell, right? And for this thin shell, okay, I am drawing it again. Suppose this is a thin shell, right? And since it is a thin, so in place of showing R1 and R2, like if normally we for the shell we define inner surface and outer surface. So if I am saying thin here, so I can consider only the one surface which is at the distance R from the center, right? So this is the advantage of saying thin spherical shell. Right. Since again I am saying it's a three-dimensional figure, so in three-dimensional figure, charge is distributed on the three dimensions. So in three dimensions, so say this is rho. So what is the value of rho? What is rho? Volume, charge, density. Right. So the charge on the surface of this spherical shell is rho. And rho is what? The volume charge density, means per unit volume on this surface is rho, right? Per unit volume. So let's see, we have a case where, okay, suppose we have a point P here and a point Q here. So we are trying to find the value of electric field at point Q at point P. So we will do it step by step. First we go for point P. So you see this point P lie outside of this shell. So if I draw a surface, Gaussian surface like this, I can draw like this, right? So if I draw like this Gaussian surface, this is my Gaussian surface. So you know from here electric field again will be like this, and the surface is like this. So this is dA, this is E. Again angle between E and dA is 0, right? So if angle is X, when we start writing EdA Q upon epsilon naught, so EdA cos 0, right? So we can write simply E constant dA, because when you go on any point of this surface, the value of E is constant. So at point P is also constant, and this is EdA is Q upon epsilon naught, right? Suppose this point is at a distance small r from this point, suppose O. So distance between O and P is, the distance between O and P is small r. So at this point P, what would be the surface area? What is the value of the surface area for a sphere? 4 pi r square, right? So 4 pi r square. So E 4 pi r square, the area of this red spherical surface is E 4 pi r square equals to, what is the Q? The charge enclosed by this surface, right? This is the surface which is enclosed, and you see the per unit volume, the per unit, sorry, this charge is on the outer surface of the shell, so it is not in the volume, it is on the surface, and surface, so we will take the surface area. You mind it, if it would be the sphere, then the charge will be distributed on the total surface, on total volume, but since it's a shell, so for the shell the charge will be only on the outer surface. And what is the outer surface? The surface area. So what we will consider? We will consider here only the surface area. Is it okay? The charge is not on the volume, charge is on the area, right? So like if I am getting anywhere wrong by explaining it, please mind it and please correct it, that this row is not on the volume, it's on the surface of the shell, because it's a shell. If it would be sphere, then it would be on the total volume, but since it is a shell, so it would be on the outer surface. And since outer surface, the area is the surface area, so the charge is distributed on the surface area of the spherical shell. Is it okay? So the charge distributed here, so we can also correct here, we can correct here like this, that this is the surface charge density, and if you want, then you can replace it by lambda, otherwise it's a symbol, so no need to change it. Okay, if you still confused, then you can go with lambda, and again this would be lambda. Is it fine? So what will be the value of q? Q will be lambda times, this is the charge per unit area, so what is the area for this surface? 4 pi r square. What is r? 4 pi r square divided by epsilon naught. So when you will solve this, you will get lambda r square upon epsilon r square. Lambda r square upon epsilon r square. Is it okay? If you want to write the value of lambda, if you want to write in terms of lambda, in terms of q, then you can also write in terms of q. So if I am saying the total charge is, suppose the total charge is q, so total charge q is lambda, which we have seen here. If I am writing in terms of q, so from this expression I can write like this: E 4 pi r square equals to q upon epsilon naught, right? So I am putting the value of a only. So what is E? 1 upon 4 pi epsilon naught q upon r square, right? So if I write in terms of lambda, so we will get this answer, and if I write in terms of q, then this answer. And this is very well known expression for you, as you have seen it in previous lecture of electric field, right? So similarly, if I go for the surface, so this is when we are talking about the P. Now we will talk about Q. At this Q, what will happen? If I am taking Q as a Gaussian surface, so you see, when we are taking this as a Gaussian surface, right? So here E dot dA is q upon epsilon naught. So again the concept is same here also. Here also what will happen? This will be E, the same will be dA. So the angle between E and dA is 0. So E and E is constant. So E into dA is q upon epsilon naught. E, what is dA? dA will be, suppose it's again I am taking, for the second case I am again taking this length is r. So E 4 pi r square for this Gaussian surface. The surface for this Gaussian surface, the area will be 4 pi r square equals to q upon epsilon naught. And if you see it clearly, you can find that the charge enclosed for this surface is 0. So in this case, the value of E will be 0. Right? So you see, in this case, we can find the value of electric field. If the point lies outside of this surface, then the value is given by the previous formula. And if we want to know the value of electric field inside this shell, so the value is 0. So like you see, a very important thing is this. Okay, we can conclude from this figure or from this expression that yes, if I am saying this is a shell with radius r, right? And suppose so you see, this is point O, this is point P, and so on. And you see, when we are moving from O to P, when we are inside this shell, so from O to P, the value of electric field always 0. So whenever we are inside this shell from the point O to point P, what we will see, the value of electric field is always 0. So at any point, suppose I want to know the value here, so you will see the value at point, suppose this point is A, so the value of electric field is 0. So from the point O to point P, everywhere you will find the electric field intensity is 0. Now what will happen at point P? At point P, the value of E from the same concept, when you will solve, you will get R square. Suppose I am saying Q is the charge on this surface. Right, so we have discussed, we have derived it, and what is the value of R here? Normally R, right? After this point P, when we go away, suppose I am saying any point, okay, let me use this point B here. So this B is any point outside of this shell. So the formula will be, this we have already derived from the knowledge of the Gaussian law. The formula is 1 upon 4 pi epsilon naught Q by R square. You see here, R is less than R. If R is less than R, so naturally this is in denominator. So and it is less, so naturally this will be more than this. Okay. So what does mean? That from point P, we have the highest value of electric field. And since we are moving away, the value of electric field will go down like this. And when this value will be 0, when R will be infinity. So when we will put R infinity, then only E be 0. So you see, this will be the graph of electric field for any spherical shell. This is the distance, right? So you see, inside the shell, the electric field is 0. At the surface of the shell, the electric field value is highest, and when you move away from the shell, the value will go down, go down, go down, go down till infinity. The electric field will be 0 at the infinity. Right? So I hope you have understood the concept of Gauss law, and you have studied the definition of Gauss law, how can we apply and what are the conditions of the Gauss law, and finally the examples through which we can understand how can we apply the Gauss law for different surfaces. Thank you very much.